quite a few people here. Hey guys, what's up? Long time no see. Well, I still can't see some of you, and that's fine. Hopefully you're all well, and hopefully you guys have been keeping up with the material I've been putting out. As you are all well aware, we are almost done with the semester, and what a crazy semester it has been. But I want to make sure that we finish strong. And while some of you have been in contact with me and I've been talking a lot, quite a lot of you have not been in contact with me. So I just want to make sure that everyone is okay, everyone is with this material, or otherwise you're all doing fine. And so I wanted to have our lectures live from now on, so I can have everyone participating. That being said, let me share the screen with you guys. And I assume everyone can see the OneNote page here.
Yeah.
Okay, cool. So this was the last lecture, what the last lecture covered. And this was talking about antiderivatives, which hopefully, I don't know, are you guys all caught up with the lectures? Do you guys remember this lecture, the antiderivative lecture? I'm gonna, I guess, just run through it quickly and then we will continue. So we started a lecture. The section is the fundamental theorem of calculus, so it's section 5.2 in your textbook. But we wanted to talk about a new thing before diving into that, which is the idea of an antiderivative, which is kind of what you would guess it is. It's kind of trying to reverse a derivative. So if you have, as you can see, some like here, a function x squared, y equals x squared or whatever, and someone asks you, what is the antiderivative of y equals x squared? You're just trying to reverse the derivative process. And in other words, you're trying to find a function such that when you take its derivative, the answer is x squared. So x squared is the answer of the derivative, right? And you want to find the antiderivative. You want to undo that process. Now, of course, a third x cubed would work, because if you do the power rule, the 3 comes down, kills that 3, subtract 1 for the power, you get x squared that way. But also x cubed over 3 plus any constant is going to work, because when you differentiate a constant, you actually get 0. And so the antiderivative of any function will have this form. There's going to be a function part of the antiderivative plus a constant, which is called an arbitrary constant. You can't hear me. Beatrice can't hear me. Yeah, leave and rejoin, and I'll see if that'll work. Everyone else can hear me, right? I'm not talking to myself.
Yeah, I can hear you.
Okay. So it's just an issue. It's a local issue, it seems. So hopefully you can hear now. Okay, so antiderivatives have this form. There's always a plus c, which we call an arbitrary constant. In fact, we call it an arbitrary constant of integration. Now, there is a notation that we have for finding antiderivatives, and it is this one. And you will, of course, note that it is actually very similar to the notation that we had for finding areas, which would have numbers here. This guy is called an indefinite integral, and he is what we use to show the antiderivative. So for example, me saying the integral of x squared dx is the same as me saying, what is the antiderivative of x squared? And then your answer is going to be x cubed over 3 plus c. The plus c is there because if there were a constant, it would have died when you took the derivative. And I made some notes about notation there. By reversing what we know about derivative rules, we could come up with some 4 basic rules. So these are just some guys you know. This is the reverse of the power rule. So instead of multiplying by the old power and subtracting 1, we will divide by the new power and add 1. And of course, the antiderivative of 1 over x is ln of absolute value of x. The absolute value is actually important there. Because when you differentiate ln, hello? Is everyone here? Because I think I lost connection for a second.
I can still hear you.
Okay. All right. So, because I have, as the host, I'm hearing like alerts when something goes wrong. There's like, it plays a sound. Okay. So, yeah, so these are just some basic rules that we can quickly find integrals, aka antiderivatives of some basic functions. And we went through some examples of actually doing that, which is what we did with here. Now, you'll notice that in some situations, you will have a situation where the integral is not so straightforward. You might have to do some algebraic manipulation or simplification to get it to look like the basic rules that you would have above. So that's an issue. And we went through a few examples, and hopefully those guys were all clear. We also looked at the connection between antiderivatives and areas, which is ultimately what the fundamental theorem of calculus was about. And it's telling you pretty much that a shortcut for finding an area is finding the difference in the antiderivative. And I went off on a tangent about what that all means and what it can tell us about calculus and life. And yeah, then we did some more examples of what we call so-called definite integrals. So this is like when we have the sign with the numbers on it. We can simply find the antiderivative, take the top number, plug it in, minus take the bottom number, plug it in. And what I want you to appreciate is that was actually us computing an area. Okay, so in other words, to find an area, instead of doing the Riemann sums, the finite Riemann sums thing, which really only gives us an approximation because we're using a finite number of rectangles, this process here will actually give us the exact answer. So that was pretty cool. So we know that the area under y equals x squared between 0 and 1, this shaded region here, was actually a third square units. And we found these guys. Now, there were some things I asked you guys to talk about. So for example, here, when we did the integral from -1 to 1 of x cubed, the answer was And we're back. Can you guys hear me now?
Yeah.
Okay. All right, technology. This has happened a couple times. So whatever. Let's try to continue. And you know what, while I'm doing this, let's not share video. Because you guys don't need to see me, just to make sure that everything is kind of going okay. All right, so let's continue. Where were we? Yeah, this one. Did anyone come up with a reason why that is 0? Were there any ideas why this would be 0? Any guesses at all? Why does that make sense? Or does it not make sense? Okay, you guys can go. I like the raising hand feature, but you can just go because I don't think anyone's falling over each other here.
Well, when you're doing the sums, you have the total of 1 over 1/4 to the 1 to the 4th power over 1/4 minus what will also be. It's 1/4 minus 1/4 basically, and that'll end up being 0.
Well, yes. So the math tells us it's 0, but in terms of us interpreting it as area, does that make sense to you that it's 0? I mean, in terms of area, what do you think is going on here? Any ideas as to that? I mean, yes, the direct calculations give me that it's 0. But the area under y equals x cubed is 0 on this interval. How does that make sense? Any ideas there?
Can I see the graph again, please?
Well, we didn't actually do the graph.
Sorry, I thought there was
So-
someone above it. My thing was glitching
Oh,
on
oh, oh.
so I had trouble getting on and everything.
So when we have y equals x squared, this was actually finding this guy was us computing the integral from 0 to 1 of x squared, right? And that is interpreted as the area under the y equals x squared graph between 0 and 1, okay? So, and we found that that was 1/3, right? So that's the area here. So now the question is, I did this integral down here and I got 0. So does it mean that the area under the graph is 0? Like, how would you explain that answer?
Okay, so with that, x cubed, like from at the interval that we're looking at, part of it's going to be under the y-axis in a total of negative numbers, and the other one's going to be in positive numbers. So if when you add it all together, it will become 0, and that makes sense. So it's like the total area itself, kind of like when you look at it under the curve.
Right. So we are looking from
to get to that.
-1 to 1. Right. So what we are essentially trying to do is we're looking at the curve in this region here. Now, one thing that, if you think about the definition very seriously, even though I didn't mention it, I asked you guys to actually think about it, is that we figure out these area by doing what? By doing these rectangles, right? So how did we define the area of these rectangles? Well, it's by the y value, right? So I take the f of x and I plugged it in and then multiplied by the delta x, and that's how I got the area of this rectangle, right? So you'll notice that because here, all these rectangles, the y values will give us a positive number. Whenever our graph is above the x-axis, we get a positive number as the answer. However, going by that definition, if I were to do the rectangles on the left side here, they will actually be going underneath, which means the f of x here, these guys are going to be negative, which means whenever a graph is underneath the x-axis, you actually return a negative area. So over here, the integral will give a negative area. Just by how it was set up, because our y values that are being outputted here are negative. So if I plug that into the Riemann sum formula, it actually gives me a negative answer, as opposed to over here. So when I mentioned earlier that, and I think I did it, where did I write it? I wrote it somewhere. Did I do it? I did somewhere. Maybe it was on the other page, which I'm not going to mess with that right now. But I did mention here that the integral gives you the area under the curve. What I want you to be aware of here is that area under, and I was looking for the part where I actually put quotations around the under here. I mentioned that somewhere. Is a net area. So this basically means when you're integrating over an interval where your function is positive, it gives you a positive area. When you're integrating over a region where the function is negative, it gives you a negative area. And so what happens is these guys, it's not that the area under this function is 0, it's just that the area on this side and the area on that side are exactly the same magnitude, but one is positive and one is negative. So they kind of cancel each other out. So this is a net effect. It's a net area. So that was the case. And in fact, something else that we can add here is that if you're integrating from the negative number to a positive number of a function, and that function is an odd function, it will always give you 0. And remember, odd function just means it's symmetric about the origin. i.e., if you take f of x, f of negative x, f of negative x is equal to negative f of x. Right, so that was what was going on here. The 0, how did you interpret it, right? What did that number mean? It's really finding areas, however, it finds the positive and negative. So this means if you are really concerned with actually talking about the magnitude of an area that's bounded between curves, you will have to worry about where the function goes negative, because you're going to have to fix that somehow. So if I really wanted to find out what is the area between this curve and the x-axis, what I would do is I would just integrate from 0 to 1 and double the answer. You'll notice that the answer would be a half. So there's actually a quarter square units of area here and a quarter square units of area here. This one, though, gives you negative. So if I made that, I deliberately made that positive, which we could accomplish through some absolute value or something, we could actually get the actual bounded area. So that was just something I wanted you to appreciate. This one is something else I wanted to appreciate, is that in this one, your function was actually what we call an even function, which means it is symmetric about the y-axis. So for this graph, if I went from here to there, it's actually going to do, it's going to actually double the area. You'll notice that this answer here was actually double the answer for the area from 0 to 1. And I want you to realize that's not a coincidence. Since y equals x squared is symmetric. So the area on the right and the area on the left are the same about y-axis. It is called an even function. So in fact, that is something that you could actually work out in general. The integral from minus a to a of f of x dx is actually equal to double the integral from 0 to a of f of x dx. So you can only do half the work if your f is an even function. And that means symmetric about the y-axis. It also means that f of negative x is equal to the original function. So if I take any x value, it will give me a y value, and the negative of that x value will actually give me the same y value. So it's symmetric about the y-axis. For the odd functions, you'll notice that if I take an x value, it'll give me a y value, and the negative of that x value gives me the corresponding negative of the y value. And in other words, that is saying f of minus x is equal to f of x. So this was just a point that I wanted to make and have you guys think about, is that the integral is actually the net area. So when we say area, quote unquote, under the curve, we're talking about net area. If your function happens to dip below the x-axis, the area, quote unquote, will be negative. Okay, so that's just some things I wanted you guys to consider for this one. But yeah, this again is what we did in the last lecture, so I'm not going to go over all of that. Let's actually go into the topic of the day, which is integration by substitution. Okay, so we'll talk about some applications later. This is pretty much the second to last topic that we are going to want to do for the semester. Which, by the way, the semester ends on, I think, next Wednesday for us. That's going to be our last class. And I wanted to talk about this and one other thing, which is a little bit of some applications of antiderivatives. But let me just say that finding antiderivatives, aka integrals, they are important. They have a lot of applications, and we're not going to talk about a lot of them, even though this is applied math. You really go into the applications of integration in Calculus 2 if you wanted to go that route. Here, though, we are going to talk about a different technique to compute integrals. So I did some examples in the last lecture of us computing integrals. And basically, we only needed these basic formulas that we're using here. Sometimes, though, the thing you want to integrate is a little bit more complicated and a basic formula won't work. So in general, the strategy that I want you guys to have in mind when you go on the test or the final and you are worried about computing some integral, how do you actually approach it, right? So you go to the test next week or whatever, and you see problems like this popping up. What do you think about? What goes through your mind? How do you actually approach them? And what are some techniques that you can use? This is going to add to that idea. So that's what we're going to talk about, substitution, another method here. Okay, so let's talk about that. You see, when faced with computing a random integral, so you see something like this, right? What do? Well, the first thing you do is you try to apply a basic rule. It just might look like something where you have a rule that will directly connect to that thing. So if you see a problem like, oh, what is the integral of 1 over x cubed, right? Now, for that, you would need a basic rule. You just realize, oh, this is x to the minus 3, and that looks like rule 1. So by rule 1, I know that that's going to be add 1 to the power, divide by the new power plus c. So that is going to be minus 1 over 2x squared plus c. And I'll get that answer, right? So this guy is just some random integral that shows up. And I can actually look at him as a basic rule. He is in fact rule 1 applies to that guy. Anything that looks like x to a number, as long as that number is not minus 1. So you'll have guys like that. Then sometimes you won't have a guy that's directly like that. You'll have a guy that you might have to simplify. So the first thing you want to do when you face with a random integral is try to apply one of these basic rules that you know. If it doesn't work, if you cannot apply a basic rule, the next step is to actually try to simplify to apply the basic rule. So an example here was one that we did last time. It's like x plus 1 all over x, right? None of these rules actually look like that guy. He does not look like a basic rule. He's a complicated function. He's not x to a power or anything like that. However, I can just divide x into both sides, into both terms on the top. And now individually, these would look like basic rules. This is an application of rule 1. That is an application of rule 2. And I can actually get to the answers that way, right? So this is like x to the 0, add 1 to the power, divide by the new power, I would get x. This is 1 over x. Rule 2 tells me that that integral is ln of absolute value of x plus c, right? So that's the second scenario that you can find yourself in. So you'll see things sometimes that just applying a basic rule directly is going to work. Sometimes you have to do some algebraic simplification to get the basic rules to work. And then yet still, there are other times that are a little bit more complicated than this, where neither of these techniques will work directly. So the basic rule is not going to work, and you can't really simplify it to look like a basic rule. Now, the good news for us is this is Math 1203, so we're only going to learn one other integration technique. So if step 1 and step 2 doesn't work, step 3 is the answer. It's always going to be this thing. It's going to be integration by substitution. That is going to be step 3, okay? Now what I want to do for you guys, and we're not going to have time to go through many examples, but at least I want to go through one in detail, is I want to teach you guys how integration by substitution is going to work. As the name suggests, we are going to substitute things in order to make our integral easier, okay? Now, what is integration by substitution? You can think of this as a reverse of the chain rule. So remember the chain rule from derivatives, that's this guy. And just the same way that we can figure out formulas for basic functions by reversing the derivative rules, we can actually reverse entire derivative methods. So the chain rule is a derivative technique. We can actually reverse that entire technique, and that reversal is called integration by substitution, okay? So how does this actually work? How do we get things to be a little bit easier? And I wrote notes here, and I'll share these notes with you guys in PDF format later on, but just breeze through this so we can go through an example and fully understand it. You have an integral, and assuming that it doesn't look like a basic rule, and assuming that you can't use algebra to simplify it to look like a basic rule, the next thing you're going to do is like substitution. That's what you're going to think. And then you're going to say, well, how do I do substitution? You're going to replace a complicating expression, quote unquote. Complicating is what makes it look ugly, what makes it not look like a basic rule. You're going to replace such an expression with a single variable. Oftentimes, this will be u. The substitution should fulfill 2 criteria. 1, it's going to make your integrand, remember integrand is the guy that you're, remember when you have an integral thing like that, the integrand is the function. So here's your integrand, right? Now, if your integrand is complicated, it doesn't look like a basic rule, or you can't simplify it to look like a basic rule. What you're going to do is you're going to look into that integrand. Whatever is making it really complicated, you're going to want to substitute with a single variable, which is the intent is to make it simpler, make the integrand simpler, right? That's the whole point. You want to get a simpler answer, okay? The next thing is, and this is sort of a relaxed condition. In 1203, this is pretty much always going to be the case, but in Calc 2, it might not be the case. The derivative of your u should be a factor elsewhere in your integrand if you ignore constant factors. And I'll explain what that means as we're going through an example. So you have a complicated integral, you're going to replace an expression with a single variable to make it simpler. After doing that, you're going to have to find the derivative of the u, which is du, because you're literally going to swap out all the x's. So you are going to need to, the point of substitution, you need to convert this to a function of u. And then you're going to have to convert to du. So you're literally substituting away the variable x, right? Everyone is going to be in terms of u's. You're going to get a new integral where u is going to be the variable, okay? So after you've chose your u, it's going to be equal to some expression. You're going to find the derivative, which is going to help you replace the dx part of this integral, okay? Now, you'll get a new integral, okay? So the new integral should be simpler, and it's simpler in the sense that it would look like a basic rule. So when I say simpler, simpler has a very specific meaning here. Simpler means looks like a basic rule. So now you should actually be able to do the integral. You'll get your answers in u's though, and usually what you're going to need to do is you want to quote unquote back substitute. So you're going to replace all the u's with the original functions that you put the u in place of in the first place. That gets your answer back in x. And if you have a definite integral, step 5 is somewhat optional, but we'll deal with that actually tomorrow, okay? So this is basically the substitution method right here. Just kind of tell you play by play how it's going to work. Now, understandably, that's confusing. And even after I work through one example, it is going to still be somewhat confusing. This is perfectly normal. Do not freak out. After a while, substitution is actually going to be pretty easy. It should be one of the easiest things on your test. So here are some integrals that are too complicated for what we've been learning so far, but we're actually going to do them using substitution. So the first example is going to be our instructive example. So let's get started on that. Okay, so here's our integral. So we're going to go through this slowly, play by play. If you have any questions, you can just chime in and let me know. Okay, so we have this guy. So the first thing you're going to notice is that it looks complicated, right? There's no basic rule that looks like that guy, okay? So, can I copy these guys down? Copy. Paste. Boom. 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 Copy. Paste. Okay. So it's complicated in the sense, that does not look like any of these guys, right? Doesn't look like any of those guys. So it's complicated. So what we're going to do is we're going to want to make this simpler. Now, hopefully you realize that you can't actually simplify this with algebra. You can't distribute the radical across the sum or anything like that. So your issue is you're going to want to replace this thing with something that's actually that will make it easier. You're going to replace a complicating expression. Now, any guesses as to what is actually making this integral complicated? Maybe someone chime in here. What would you want to replace with a single variable?
I would want to replace the root of 1 plus x squared.
Yeah, or let's just be a little bit more careful, because I don't want to have to, ultimately we're going to have to take derivatives, so let's make it actually simpler. Let's replace this. This here is complicated. How do I know? Well, if it were a single variable, if I had like x times the radical of x, that's actually no problem, right? So if there was a single variable, it's easier with a single variable here. Because I could actually just write this as powers, right? This would just be x to the 3/2, and I could integrate that easily. So this is what makes it complicated. So what I'm going to do is I'm going to replace that expression. So set u equals 1 plus x squared. That's going to be your first step. Now, of course, we're going to want to replace the dx. So what I'm going to do is I'm going to actually differentiate. So your du is going to be derivative of this 2x dx. So you're going to have to remember your derivatives, obviously. Now, what happened here? Now, we don't really write this, but I'll just show you what happens here. If you take the derivative of both sides with respect to x, du dx would be 2x, and then you multiply by the dx. But we always just actually jump to this line. We don't normally show that. Now, there are a couple ways that you can proceed here. I'm going to go with, especially since we're doing this online, I'm going to go with the one that I have found, statistically speaking, that students can follow along a lot easier. So the next thing I'm going to want to do is solve for the dx. Right? There are other ways to think about this step, but that's what I'm going to do, how I'm going to do it. Next, solve for dx. Okay. Then we are now literally going to replace all these guys. Okay, so this gives me, go back to the original integral. I'm going to start swapping guys out. Okay, so the 1 plus x squared, that is now u. My dx is now du over 2x. And the x I didn't replace with anything, he just stays. Okay, so that's what's going on here. So the u is this part here, that gets replaced with this part. And then my dx is this part here, that gets replaced with this part. The x wasn't, I didn't do anything with the x, so that's just going to stay as an x. However, what you're going to notice now is this x and that x are going to cancel, right? And this is why this criteria was important. The derivative of your u should be a factor elsewhere in your integrand. So the derivative here is 2x. I need a 2x somewhere else. Now the constant factor doesn't actually matter. The fact that this is 2x and x, that's not really a big deal. But the fact that there's an x there in both the du and the original, that's good, because it means that something like this will cancel. If you're off by a constant, don't worry about it, because we know that constants factor outside of integrals. So this 2 here, I can bring it outside. And our integral now becomes that guy. And now what you're going to realize is that, gasp. Looks like a basic rule, this guy. Our integral is now easier. In fact, now I know how to deal with that. This is going to be u to the 1/2 du. We are going to find the antiderivative of that, which is, I'm going to leave the constant, add 1 to the power, divide by the new power, so that becomes 2/3 plus c. My 2's are going to cancel. And so I would have 1/3 u to the 3/2 plus c. Now notice that this is the answer in u's. So what you would do now is what's called back substitute to get the answer in x. So what I'm going to do now is originally my u was 1 plus x squared. So I'm just going to replace that u with 1 plus x squared. It's starting to rain. And that is your answer. And you can check, if you were to differentiate this, you will actually get this function. But that's your answer. I'll just make a note of that. You can check that if you take the derivative of 1/3 1 plus x squared to the 3/2 plus c, the result is going to be x times the radical of 1 plus x squared. Okay. So let me do one more example, just run through it very quickly, and then you guys can let me know if there are any questions, which we'll probably have to deal with tomorrow. So I'm going to run through this one quickly so you can just see one without all these markings all over the place in really quick thing. So I'm going to do this one. So I'm looking at this, looks very complicated, doesn't look like a basic rule. And so I'm going to essentially want it to look like a basic rule. So I have this guy, fraction, can't simplify it because I can't split a fraction across the denominator. So what I would do is I would realize, you know what, this denominator makes it complicated. So what I'm going to do is let u equal the denominator because that's making it complicated. Then I'm going to find my derivative. Derivative of e to the x is e to the x du dx. Now I'll notice here that I have e to the x dx. And in my original function, I have the e to the x dx right there. So my derivative is a factor somewhere else. So that tells me it's a good substitution. So then what I'm going to do is I'm going to solve for dx. And then I'm going to plug into the integrals. So the e to the x was over here, the u is on the bottom, and my dx is du over e to the x. What's going to happen now? My e to the x's are going to cancel, and now I end up with this integral. 1 over u du. And hey, that's a simple integral. It is a basic rule. That's ln of absolute value of u plus c. And I back substitute to get the original answer in x's. My u was 1 plus e to the x. Which technically you don't need the absolute values here because inside is positive, but I would leave the absolute values because it's never wrong to leave them, but you're potentially wrong if you don't put them in. So absolute value, very important. I should mention that. Well, in general, it's very important. Okay. So this is integration by substitution. I have a complicated expression here, which, I don't know, maybe I should write that down without all the markings. So I have the integral of e to the x divided by 1 plus e to the x. And this is how I would do that integral via substitution. So far, are there any general questions about the method or anything? Do we kind of get questions, concerns? Anyone out there? Bueller? Can you guys actually hear me? I don't know.
I can hear you. I'm
Okay.
Questions.
We're-
sorry. I don't want to scare you or anything.
Wait, I don't have any questions about the problems, but are you gonna still keep uploading YouTube videos, or are we gonna do lessons through like the Zoom calls?
So it's going to be both. So I do want you guys to be here as I'm teaching. But I will also, I'll post a PDF of this, and I'll also send you guys a recording.
Okay, thank you.
Okay?
So, sorry, I have another question as well.
Yes.
When you sent out the links for the Zoom calls, I don't know if anyone else had this, but in the emails it said, and like when you went to register for the class on the Zoom, it said that it was in Pacific time, not Eastern time. I don't know if anyone else had that or if it was just me because I live on the West Coast.
Oh yeah, I don't know, but it is during our it's 11:30 a.m. Eastern time.
Okay, that's what I had thought. I was just confused by the Zoom saying a different time zone.
Yeah, so if you're on the West Coast, that might be an issue, but it's
Yeah.
I'm definitely giving you Eastern time here. Anyway, that being said, think about what happened. I'll give you guys a PDF of this pretty soon, and give you guys access to the recording as well. Go over it again slowly. If you have any questions, we can pick them up tomorrow. Tomorrow we'll also do the rest of these examples up here.
Are we still planning on having our test coming up on Wednesday?
So one thing, I would like you guys to actually try this for tomorrow to make sure, because you might not be aware that you have questions until you actually try some. So actually try examples C, D, and E for tomorrow. Yes, we're still having tests. It is still on Wednesday, and it will be an online test. So I'll give you guys more details about that. In the meantime, there are mock quizzes posted on the class webpage. So you can practice one topic at a time. And I will also post a review for the test, which will be on, I'll post that, I think, tonight. So you'll be able to practice starting tomorrow. But yeah, the test is still on and all that good stuff. And I'm not sure how the final is going to go, but I'll probably use the same protocol that I'm using for the testing. That being said, I'll have to give you guys more.
Just to clarify, is
Yeah.
the test is next Wednesday, the 29th, right? Not this Wednesday?
Correct.
Okay, thank you.
As the last test, it is not cumulative with test one. So it's everything since test one. So it's pretty much applications of derivatives and everything about integrals all the way up to substitution. So pretty much the test will cover up to what we did today. Between what we did in test one and what we did up to today. But that being said, I will let you guys go. If you have any other questions, we'll bring them up tomorrow, because I know some of you have other classes to run too. So yeah, I'll see you guys tomorrow. We'll check in. And I'll give you more information about testing in the end of the semester. But we had some technical difficulties. I don't want to spend any more time talking about administrative stuff. So take care, guys. Be safe. I will actually see you guys. I guess tomorrow. So bye. Take care.